Welcome back. Now, the good thing with thermodynamics is there is absolutely nothing you have to memorize, okay? It's all, most of the time, at least for the purpose of this class, it requires absolutely zero memorization. So you do not have to prepare hard. All you have to know is where to put what. And I don't think that I would call it necessarily memorization like some of the other things you actually have to memorize. So one of the thing is, remember I told you delta H, right? Now that is enthalpy, okay, which is for the reaction. And if you see delta H 0, that's nothing but standard enthalpy. Okay, I don't want to get into it all that much, but standard enthalpy, or some people call it standard enthalpy of formation. But just so you know, there's a difference between delta H and delta H0. Delta H is for the entire reaction, but each individual component of that reaction could have its own standard enthalpy, right? Now the question is asking, calculate the value of delta H0 for the reaction. Okay, this is the reaction, okay? And you are provided a list of values. That is, you are provided enthalpy of formation of ammonia, CH4. O2 is missing. You would wonder, hey, there's O2, but there's no value. Okay, any molecule, any element that's diatomic of its own kind, that's O2, okay, H2, N2, it's diatomic, the value is 0. That's why it doesn't exist. So O2 equals 0 kilojoules per mole. Okay, I did purposefully pick this problem because I want to say it. Any element that's diatomic is in its pure state. That means its value is 0. And we have it for HCN, and we also have it for water. You see, all of these elements have at least two different elements combined together. But when you have a same element combined with itself, then its enthalpy of formation is 0. Again, we're not going to go into detail on why that's the case because that's beyond the scope of this particular series of videos. Now, to calculate delta H, I'm going to write a generic equation which is applicable to a lot of other problems in this series. Is adding sigma, if you remember sigma from your math classes, sigma of enthalpy of formation of products minus, I'm keeping this simple even though there's a few more things in here that I'm not writing because again, I don't want to make this generic thing really super complicated. Okay, there's something I'm missing here. I mean, if people are watching this on YouTube, they're probably going to immediately jump to a conclusion, oh, you're writing it wrong. No, I'm not writing it wrong. I'm keeping it simple. I'm going to explain it as I work the problem. All right? Okay, as you see, P is products, R is for reactants. That's very important. Don't mix it up. And sigma stands for sum. All right? So how do we calculate this delta H0? Well, I have given you all the values. Now, there's one thing I do want to point out here is I will not give this equation balanced. Okay, so it's your job to balance. Here I am using a balanced example because, you know, that way I don't need to balance and work it out. I just want to keep the video time as little as possible. All right, so I'm going to open a giant bracket. Okay, so it doesn't matter which product you want to pick. Let's start with HCN. The value for HCN is 130.5. Now that times 2 because there's 2 HCN. Okay, open as many brackets if you have to, plus there's 6 water molecules and the value for water is negative 285.9. It's necessary you put enough brackets, otherwise you're just going to have, that's it. This is the product. You see, I did not put the mole here because it has confused some students in the past. Instead, keeping it too generic and then adding components as seem to be worked better. So don't forget the 2 and the 6, okay? So we're starting with products minus. Again, for reactant side, we're starting with NH3, which is again 2 times negative 46.19. This stuff is easy. Like I said, you do not have to memorize anything. Plus again 2 times negative 74.86. Close the bracket, close the big bracket. This is for reactants. Now, it's highly recommended you use as many brackets as possible because you can literally do all this calculation in one single straight. So it's 2 times 130.5 plus 6 times 285.9. But it's negative technically, so it's 285.9 times 6 minus 2 times 130.5. So it'll be negative. So the reactant side, this whole thing is negative 1454. Oops. Sorry, let me get the full screen on. 1454 0.4 kilojoules per mole, are actually just kilojoules because we got rid of, when we multiply the number, it becomes just kilojoules. This is the product side, and then we do the same for the negative side. So it's basically two negatives, so we can add them. Again, I'm not going to teach that level of math here. That's something you should already know. So 74.86 times 2 plus 2 times 46.19. So that's negative of negative will be positive of 242.1. And keep in mind, this is negative, so 1454.4 plus 242.1. The whole thing will be negative 1454.4 minus 242.1. So it's negative 1212.3 kilojoules. It's no longer per mole because when we multiply by 2 or these numbers, it automatically becomes this. So this is the value for the delta H0. Again, I will provide this generic equation in the appendix. All you have to remember is balance the equation and then multiply each of the appropriate value that are either on the product side or reactant side by the appropriate value in front of it, and then just do a subtraction. Keep in mind, because of the sign, some students don't know how to do the actual calculation, which is not something I'll be happy to help you, but this is something I expect you to know it already. So this is the answer. And what do you think? I gave in the previous video delta H, if it is, I know it's delta H0, but what do you think? Is this overall reaction exothermic or endothermic? Good, it's exothermic. Why? Because the sign is negative. All right, I'll see you back with another video, so stay tuned.